Okay, so let's start. So last time, okay, before that, remember tomorrow we are going to make use of the discussion section slot, so be there. Anyone still waiting for hardware other than you guys? So that I ordered should arrive in a day or two, okay? Anyone else waiting for anything relating to project?
Yeah, we're still waiting for our maintenance board, but I think they're.
So I think all the other parts of the order are here except the maintenance.
It has not arrived or it was not been ordered yet?
It has been ordered, it has not arrived.
Okay.
Yeah, we're not gonna do it this month.
Okay. You know, I'll try to dig out to see if there is any in my office because how many you have in the lab? Two? Like total right now. How many are accounted for?
One I have given to him.
And one,
One is with Raj.
so there are two accounted for right now, right?
Yeah.
I'm pretty sure I've ordered a lot more.
And there are three boxes, so one is in the
Okay, so I'll look around and see if I can, okay. Okay, great. So last time, towards the end, I started covering 802.11 as an example of medium access control protocols. So basically, the analogy I'd drawn was that think of it like it's a distributed scheduler for nodes which are trying to share a resource, in this case the wireless channel, compounded by the fact that unlike wired networks, here you don't even you can't easily see whether your transmission is successful or not. Okay, so because you cannot hear your own, you cannot kind of detect a collision in the packets. So what 802.11 and similar MAC protocols, there are many systems use something akin to this. What they basically do is they start out with this notion that I'm going to look if some transmission is already going on in the channel, and they do that for a little bit of time. So that's the DIFS interval that you have. Then the packet is transmitted, and then meanwhile what happens is anyone else who wakes up, and if they find the channel who wants to transmit, if they find that something is going on in the channel, then they are going to wait until the current packet ends, and then some more, another interval of time, and then they do a random wait, and that random wait is to desynchronize things, because otherwise, like if a whole bunch of people nodes wake up and find the channel busy, then they're all waiting for it to free up, and then if they immediately were to start transmitting, then packets will collide. So you want to just stagger them out. Okay. Then on top of it, there is a possibility of an acknowledgement. So the idea is that if you want more reliability, then you do link layer acknowledgements. And there has always been this kind of is link layer acknowledgement worth it or not? So in networking, there's a concept called end-to-end principle. Okay, anyone heard of it? No. Okay. It's kind of one of those things which becomes like sort of that if you violate it, it's kind of heresy, it's kind of principles of good design. So there's a paper from 80s and 90s out of someone, David Clark from MIT, but basically what it says is the following, that there is already acknowledgements that take place at the level of transport layer, like your TCP layer, right? So why, therefore, should you bother doing any sort of retransmission at the link level, okay, at the level of a single hop, if you're already doing it end to end? And that probably assertion was true for wired links because they tend to be reasonably good. But when it comes to wireless, since wireless links can often be quite bad, so there is value in addition, doing a lower level acknowledgement so that you can repair things kind of pretty quickly. Okay, so so there's kind of this tension from a high level viewpoint, end-to-end principle, that leave things which are already being done end-to-end right there, don't and keep the links simple, to one where maybe the channel is bad, there is value in having an acknowledgement. The other thing to remember is that anytime you're transmitting a packet, the longer the packet, the higher the chances of the packet not making through, just probabilistically, right, for the same bit error rate. So if you're sending long packets, maybe again acknowledgement is worth it. So 802.11 has provision for that, so acknowledgement has to go out. Now the question becomes, how do I distinguish between those other packets who were waiting to transmit? Remember, the protocol was that once the transmission ends, they have to wait for a certain amount of time. So the trick out here is that the protocol defines two time intervals, SIFS and DIFS. DIFS is what is between two ordinary packets, and SIFS is what is between a data packet and its corresponding acknowledgement. So the idea is that if there was an acknowledgement it's going to be, it has to be sent out with an SIFS interval. So going back to earlier in the course, we talked about timing constraints and such. This is an example of a maximum timing constraint. That is, the receiver, if it has to send the ACK, has to send it within SIFS period of time. And that way the protocol works out because DIFS is designed to be longer than SIFS. So everyone else who's waiting, they will in that period again and see that something has begun to go on. So the other potential transmitters, they basically keep sniffing the channel during this time to see if something, if it again gets occupied, and it will if there is an acknowledgement. And then again, kind of the whole process will start. So after ACK, you will wait for a DIFS. You also see there is also PIFS out here. It serves another role, so it's called priority interframe spacing or something like that. But the idea out here is that it is used by packets which need higher priority than the ordinary packets. So you can think of this time interval as playing the role of priority, right? How much you wait is indicative of how much priority you have. So ACK packets have the highest priority because they have the shortest interframe. In fact, it is called short interframe spacing. PIFS are the next highest priority, and DIFS is the lowest priority. And the idea behind PIFS is that there is another class of traffic that exists in 802.11, which basically is done periodically. Okay, so they get priority over kind of the ordinary packets which are just contending for it. So this basically becomes a priority mechanism. Another priority mechanism is via this contention window. So you can also imagine that if you want to give some node higher priority, then they can always choose to select. You can bias their random number. Lower priority nodes can have a longer contention window to work with, and so they select a random number over a longer interval, and higher priority node can select it over a shorter interval. So there are few of these knobs that you can that the protocol exposes that one can use. So those Wi-Fi systems which prioritize like voice over IP traffic, for example, your telephone calls or video traffic, they often make use of the PIFS. So they kind of identify those kind of traffic and then basically give them in effect a higher priority so that they get lower latency characteristics. So those are the interframe spacing. I think I've sort of covered everything else. That you back off for a bit by choosing a random number within a contention window, and the contention window you keep expanding. So you start out with a small contention window, size 7, but if the first round of contention again results in a collision, okay, then you increase it so that kind of you again are sort of lowering the burden on the channel in effect. Yeah, okay. Something to note out here is that in this approach, excuse me, in this approach, the receivers are sorry. Yeah, so in this approach, the receivers are kind of always listening. And recall when I shown that picture of a radio, one of the challenge, and in fact earlier when we were talking about MAC protocols in context of time synchronization, receive takes a lot of power too, particular and relatively speaking, in short range systems or medium range systems, that can dominate. So you probably don't want to avoid, you want to avoid the situation where you're just wasting energy listening, and that's what 802.11 by default, the way at least I describe the protocol, is doing. So you also want somehow some concept that you are not simply just blindly listening. The other thing to keep in mind is, going back again to the timing diagram, even when you are sniffing the channel, like is it busy or not, again you have to turn on the receiver. So essentially Idle listening is basically as expensive as actively receiving because you are still kind of keeping most of the radio up. And transmitting is going to be more expensive in Wi-Fi, but it's going to be a function of the power. So in the case you are operating Wi-Fi at extremely low power, maybe you can, in that case, receiver can begin to dominate. But usually Wi-Fi systems are designed for like building type coverage, and also they do transmit at reasonably sort of large power amounts, so transmit does tend to dominate. So how does this MAC and power consumption kind of play out? So if kind of step back and see like what are the things that can result in energy consumption and therefore should be factored in. So firstly, this idle listening, right? If I am not transmitting and not receiving but just passively listening, then it's waste of energy. So goal number one, we should minimize that. Second thing, anytime packets collide, that's wasted energy, right? We sent the packet and to no avail. So collisions are the second evil. Third one is control overhead. So for example, packets like these, the ACK protocol, or there are other things in other protocols, like before I will send a packet out, I'm going to send request to send and clear to send. You might have seen these kind of protocols in kind of some older settings. So any extra signaling packets, as they are called, that is packets which are not carrying your actual payload data but whose purpose is to help you mediate the whole channel, they are pure overhead also. Also overhead, needless to say, is also the header part of the packets, right? Anyone knows like how large the headers are in your IP packets that we send over Ethernet? Oh no, you're way far off. Many tens of bytes. Okay. The challenge out here is the following. Okay, it's like 30, 40, 36 bytes, something like that. It's kind of a huge number. Okay, and then this is not even accounting for kind of that packet is sitting inside the MAC frame, which has its own thing, and then the preamble that we talked about. So if you have a sensor sending a byte of data and then you have 50 bytes of header overhead, then your efficiency is 1/50. So that's also part of the overhead. So going back to like the example of the ACK packet, if I am sending very small packets, then perhaps the ACK packet is not worth it because I might just handle. So let's talk about it. So let's say I'm worried about a high packet loss rate because the bit error rate is too high. So one approach is this, right? I do an acknowledgement, and if the acknowledgement doesn't come, the transmitter sends it again. Is there something else you can do? What are the other strategies you can think of to make the link more reliable? Any thoughts? Yeah.
Some kind of timeout period.
Well, timeout is going to be with the ACK, right? I mean, so with the ACK, the typical protocol would be that the sender will send the packet, and then if the ACK doesn't come during certain time, then it's going to say, okay, it's lost, I'm going to retransmit, right? So now there is a chance that the packet did make it through, and it was the ACK which was lost, right? I mean, so that's an added complication, but in this case, basically we are saying that ACK gives me extra overhead. Is there something I can do to increase the chance of the initial packet going through? Okay, good point. So instead of sending one bulky packet, I send smaller packets, right? The trade-off though there is that if my overhead of the packet is fixed, like the header part of the packet, then I'm adding more header overhead, right? So that's a trade-off, but each individual unit has a higher chance of making it through because it's shorter. So yeah, there is probably going to be some optimum packet length in which you should chunk things up. What else? Is there something else that you think you can do? Okay, yeah, great. Error correcting codes, right? So error correcting codes add extra bits. They increase the packet length, but because of the way the coding works, they increase the overall resilience of the packet. And you can do error correction within the packet, or you can do across packets, like you can send parity packets. Instead of just having parity bits within a packet, you can send parity packets, or you can even do kind of really naive, trivial replication coding, right? Send the same packet twice, one of them makes through, right? I mean, so you can do ideas like those also. So again, sort of these are various strategies one can try. Third, so this control overhead kind of relates to handshaking and relates to reliability, right? I mean, all of these things come into play. And the final thing which results in power consumption is overhearing. So I transmit a packet, it's meant for him, but everyone else is listening and hears it, and so your radio, the receiver circuitry works and all and wastes energy, even though the packet is targeted only at one particular node. So overhearing is costly, and in fact, it can also be a source of attacks on the systems, because I can maliciously cause radios to wake up by just sending out random traffic, and it will cause these things to wake up, listen, oh, it's not for me, go back to sleep. But just the act of waking up and listening burns energy. So 802.11 is not very well, is at least in the form I have described. It has some additional features, but in the form I described, it's not very good in this on these fronts. So if you so the net result of this, and this is kind of a pretty old simulation someone had done, but it shows that what happens if you ignore these issues. So on the left hand side is a system running the standard 802.11 MAC, the way I described, and it has a bunch of different schemes for routing data, okay? And there is something called diffusion, there's something called omniscient multicast, as in kind of we somehow know a tree-like structure, so kind of just do optimally forwarding the packets. And then the third one is this naive flooding, which we talked about last time. I kind of flood the network with it. And you see that basically the differences between kind of smarter routing schemes and the dumber routing schemes basically disappear because the MAC protocol is so inefficient. On the other hand, there are MAC protocols which are designed to be energy aware, as in they kind of do those things to mitigate those effects. There you begin to see the effect that flooding is inefficient. On the other hand, things like diffusion and all end up being more efficient. So the point I guess I want you to take away from this thing is that there is a lot of coupling between the different layers, what's going on in the physical layer, what's going on in the MAC layer, what's going on in the routing layer. And you really ought to think of these things as kind of core design, because otherwise in isolation a single layer may seem smart, but if the other layers are not designed appropriately, then the overall system can be quite inefficient. So that takes us to the next thing, routing. So this issue of energy awareness and all and timeliness enters at every level of the system, right? So at the physical layer, at the MAC layer, and then at the routing layer. So routing layer's job is to get packet from node A to node B across a network. Now, getting from node A to node B is trivial if everyone could hear everyone, right? But that's not how the networks are, so we have to face this. So traditionally, I mean, what happens inside computer, and that holds true for embedded systems also, that applications run in the user space, operating system provides networking as a service, okay, through some APIs. So like sockets, for example, I'm sure you must have used them at some time or the other. Nowadays, programming languages provide even higher level abstractions, like I can simply say get something from a URL, and then under the hood all sort of stuff happens. So abstractions have gone up and up, but point is that programming languages and OSs provide various kind of APIs and all to do it. But the essence of all of this deep down is that within the network, within the operating system, there is a protocol stack, so-called TCP/IP stack, so which provides you TCP and other transport protocols like UDP and others, IP layer, which handles the routing tables and all, data link layer, which is where kind of framing, MAC protocol, these kind of things happen, and then finally the physical layer. Okay. So traditional network systems, like in case of the internet, as I mentioned last time around, kind of they are organized hierarchically, so that if I need to send a packet, like if you look at an IP address, then you can kind of, the more you move towards the least significant bits, then the more specific they are. So there is kind of a 128.97.92.1 is contained in 128.92.97, for example. So you can think of it like a hierarchy, and when you route, you only need to maintain pointers to entire networks as opposed to every machine. So the tables where you store this information can be very compact, because all I need to know is how to get to a network, a subnetwork. And then once I reach there, then the router in that subnetwork can route within that network. So you organize things hierarchically. As I pointed out though last time, wireless networks tend to be different. So these multi-hop networks and all that we have, the challenge there is that it's a flat network. So again, let me kind of step back up and draw another distinction out here. So in these traditional networks, what happens is when finally you do reach the local area, then it's effectively a broadcast network. Not quite true, but almost. So every machine can conceptually hear everyone. Okay, so when it hits the Ethernet, let's say like LAN in your home or in your lab, then every machine can listen to everyone, so there's no more any routing problem. Okay, as long as the machine exists, once the packet reaches the gateway to your network, then essentially the gateway can send the packet to any machine on your local area network. The reason I say it is not quite true is that nowadays Ethernets have become pretty smart. So it used to be that long ago, Ethernet meant a piece of coax cable and everyone was sitting on it. Nowadays, Ethernet are switched networks, right? You have wire running or cable running from your machine to the Ethernet box. And inside the Ethernet box, there is again kind of something like routing going on, except at a lower layer, at the MAC layer. So, but without getting into that, to the first order, you can say, as long as I can route to the gateway of your local area network, I'm good to go. But not in wireless, because this is how a wireless network looks like, okay? And moreover, the topology is changing, links are coming and going, so it just becomes a trickier thing. So every little node in the network, in a network like this, has to provide the ability to route packets. And even if nodes are not moving, connectivity is often variable. There are several reasons for it, but perhaps the biggest one is the environment changes, okay? Like a door gets shut, someone puts a new metal cabinet, window gets closed, all these kinds of, or even like too many people in the room, okay? We are bags of water effectively, okay? So all these things affect the transmission, and therefore connectivity kind of varies over time, and therefore the network needs to be able to adapt to that. Another challenge is, and kind of goes back to, there is a coupling with power management. Remember, we save power by shutting things down, but if a node is shut down, then it cannot offer the routing services. So it's easy to say that, okay, one of the nodes is, each node has to offer routing services, but they're not always available. So unlike our regular network infrastructure where routers don't go to sleep, or Ethernet switches don't go to sleep, again, not true, but not quite true nowadays, but in wireless, that's a much more serious issue. The reason I say it's not true even for Ethernet is that even for wired networks, even though they are plugged in, energy has become a huge consideration. The reason energy has become a huge consideration is that this is infrastructure which is idle, and if it's always consuming power, then there is kind of a societal thing. So even though they are not operating on batteries, they are just burning power. So nowadays, when you go and try to buy a Ethernet switch for your home or router, right? I mean, they often say green Ethernet, okay, and that's basically Ethernet which does shut down. But Ethernet still has an advantage in that it's working over wires, so I can send some signal over the wires to still arrange for things to be woken up. A lot harder in wireless, because if the radio is asleep, I cannot wake it up. So something that we saw sort of earlier as well. So that affects routing, and then on top of it, the kind of traffic patterns that exist in IoT systems are kind of different than the traffic patterns you tend to see with regular laptops and all, okay? Dominantly, the traffic that you will see from a laptop at your home is going to be some server on the on the internet and kind of downloading traffic. Whereas the traffic among these IoT devices is often a lot more peer-to-peer heavy. Okay, so just those traffic differences come into play. So the routing problem has a different flavor out here, and what has happened therefore is lots of very specific protocols and all have been developed for it. Some designed for mobile scenarios and some designed for kind of non-mobile scenarios. So there are, like in this list that exists of various wireless technologies, there are some I'm sure you already would recognize because they exist in our standard devices. So 4G LTE, Wi-Fi, Bluetooth, I'm sure we all use them, but in this alphabet soup there are some other radios technologies which are more encountered in IoT / embedded system things. So Z-Wave, Zigbee, LoRa, and ANT are kind of examples of that. So ANT is kind of like a subset of Bluetooth in a way, in the sense that it's a precursor of Bluetooth. Probably the only place you would find ANT nowadays is your older exercise machines, okay, like those which talk to like heart rate thing coupled to your treadmill, and also the older one were often using ANT. Nowadays sort of even they have switched to Bluetooth. Z-Wave and Zigbee are what are encountered quite a bit inside in building kind of settings. So Z-Wave is very common, but it's not a standard in a strict sense, but rather a proprietary thing from a company, but it got popularized quite a bit. So a lot of products, smart switches and all that you'll find at Home Depot and all, they're basically Z-Wave based. And what it does do is, besides defining the low-level protocols and all, it also defines a routing thing. So it's a multi-hop network, so you can install these things anywhere in your home, and kind of it creates this routing. And also it has a method of pairing things. So one of the challenge also is how do you add a device to these things in a secure manner. So it kind of does that. Zigbee is very, again, you'll find them at homes and all, but Zigbee is not something you will find in switches and all so much, but you will find them in like light bulbs, smart meters, smart fridge. If you have any one of these interconnected washing machine or fridge and all, they're probably Zigbee based, because they have the ability to then in turn talk to your meter, for example. Okay, and then electric utilities use Zigbee for collecting data from meters, so meter to meter routing. So like nowadays a lot of electric utilities, the meters themselves form a network so that they can talk to each other, they can send status updates and stuff like that. So that's Zigbee. And then finally there is LoRa, which stands for long range wireless, and it is for city scale sensing or city scale IoT. Okay, so these are kilometers, like 10 kilometer type thing, but much lower data rate. So Z-Wave and Zigbee are megabits, and this is 10 kilobit type thing. Okay, so they serve a very different purpose. The ranges are obviously hugely different. Although for Zigbee also you can find radios which burn more power and can go to a mile or so. Okay, but kind of not really designed for this thing. So LoRa is what has penetrated. So a lot of like cities which are calling them smart cities, like San Diego, for example, has this installation of smart electric poles. Actually, LA is also doing something like that. So what cities are doing is every time they're replacing the electric poles, they are replacing them with these smart poles, and basically they run fiber to it, and then they rent out the poles, so to say, for other companies to install sensors and communication equipment and stuff like that. Okay, so that's an example. So LoRa, oftentimes they install kind of base stations like that. But all of these technologies also sort of compete with each other. So like at least here in LA, the Time Warner Wi-Fi is, or whatever, the Spectrum Wi-Fi is kind of quite prevalent in the denser areas. So Wi-Fi in urban areas is certainly sort of an option, but the receivers tend to be more power hungry. The LoRa, the idea is that these are designed for devices which can last for years. And there are several things which make it that way. So besides the low rate, I already said that they are more in kilobits per second or even fractional kilobit per second. LoRa also operates at much lower frequencies in 900 megahertz band and 433 megahertz band, as opposed to Wi-Fi, which is in gigahertz, right? Why do you think lower frequency helps for power? Anyone? Huh? Say it? Can travel further. Yeah, they can penetrate through things better. So for the same distance, you are basically better off that way. So yeah, so these are the things. And then under the Bluetooth camp, there are two different Bluetooths almost. Like you can almost think of them as they are really kind of very separate standards, but they are all called Bluetooth. So there is kind of this Bluetooth designed for high rate thing, the so-called Bluetooth classical or classic, and then Bluetooth which is designed for very heavily duty cycle sensors, like for sending stuff like a heartbeat or stuff like that once in a while, and that's Bluetooth low energy. And that has, so you can again say like the classic Bluetooth is meant for many megabits per second, whereas BLE is meant for let's say 10 to 100 kilobit per second range. So Wi-Fi, as we know, it's kind of very prevalent. There are a whole alphabet soup of them, many different standards, and many that I don't even list out here because it's a continually evolving standard, operating in 2.4 and 5 gigahertz bands, very high speed. So the newer Wi-Fi A2.11 AC can get to bandwidths of, I think if I'm not wrong, 2.3 gigabit per second or something like that, but so pretty high. And the problem also is it's also very high power consumption. So you will not find them generally in battery operated devices meant for lasting for years. You'll find them more commonly in devices which are somehow powered, so like cameras and stuff like that. Okay. Bluetooth, megabits per second, shorter range. I already mentioned there is this BLE, which is designed for even lower rating. The interesting thing which is happening in Bluetooth is that there is a Bluetooth mesh that has emerged. So Wi-Fi technically also has mesh, but it's really not very commonly available or used. Okay, whereas Bluetooth mesh under the so-called Bluetooth 5.0, which sort of began to emerge over the last year or so, that is expected to penetrate quite a bit. A2.15.4 is what that Zigbee thing was. So it's a standard. The 15.4 standard defines the physical layer and the MAC layer, and then Zigbee on top of it describes all the way up to routing and application and stuff like that. So it is, like I said, in smart appliances and all, extremely prevalent. So the way this works is, so Zigbee is built on top of the 15.4 standard, and the 15.4 standard in turn operates on those ISM bands, so one in the sub gigahertz range and one in 2.4 gigahertz, is designed for lower rates, relatively speaking, 250 kilobit per second, and there is also 1 megabit per second standard, I think, for devices which are supposed to last for a small number of years. Uses mesh networks to transmit over to cover long distances, and it's basically in like smart lighting industry, smart meter industry, these kind of things, or medical devices. That's where it has seen the penetration. And the key thing that they did, and something that Wi-Fi doesn't do, very rapid wake up. So the radio receivers are designed so that they can duty cycle very rapidly. And as we discussed earlier, both in CPUs and again in context of radios, that's a metric. For a device that you're going to do duty cycling, the wake up time is important. So traditionally radios, Wi-Fi inclusive, were not designed for that. They were designed for bulk transmit efficiency as opposed to rapid wake up and going down. The other thing is that they were not designed for sending small number of bytes. So I gave the example earlier, if I want to send a single byte of temperature reading and I'm encapsulating it in many bytes of data, then that dictates the efficiency. So these radios were designed for that. So for example, you see ZigBee, the wake up latency is 30 milliseconds. Bluetooth, classic Bluetooth, not BLE, had latencies of waking up and synchronizing of seconds. And Wi-Fi can be the same thing. I mean, you probably see it also. So again, there's obviously protocols evolve and also Wi-Fi and Bluetooth have added features like BLE in case of Bluetooth, but ZigBee, which is now probably around 15, 16 years old, was designed from the outset with heavily duty cycle devices in mind, okay? And part of it was that the radio circuitry was the modulation schemes were picked so that you could design radios which could consume low power and can rapidly wake up. So everything kind of couples together. Wi-Fi is intrinsically less efficient because the modulation scheme that Wi-Fi use require highly linear amplifiers, and highly linear amplifiers are intrinsically more power hungry, and therefore everything kind of follows from that basically. It's also optimized for bulk load transmission, so the packet headers are sort of longer, and also if you're sending tiny little sensor data, Wi-Fi is a pretty sort of ill-suited for that purpose. So yeah, go ahead.
So it says 2.4 gigahertz worldwide and not US, but is there any interference with Wi-Fi?
Okay, excellent question. So remember last class I said there was this additional stuff that Wi-Fi still has to obey. So that's what this issue comes in. So part of the condition of these free bands, so-called the ISM bands, is that you have to tolerate whatever interference that exists. So in this band, in these bands are other scientific instruments, medical instruments, and as you could see, ZigBee and Bluetooth and all, they're all operating. So in addition to the protocols, there is a etiquette, as it's called, that FCC specifies. Okay, and part of those etiquettes are things that you are supposed to do. Like for example, you cannot transmit at more than a certain power. For example, you need to back off if there is something going on. So there are all these additional constraints, and all these protocols are designed to be compliant with that. So because they're all obeying that etiquette, so the interference isn't there. For example, in the 2.4 gigahertz band, there is stuff in our home. Anyone? Microwaves, yeah, right? Because microwaves work by, how do microwaves work? Huh? How do they work? How do they heat? Huh?
They send out waves that make the water particles.
Okay, and what's the resonant frequency of water molecule? Guess what? It's in the 2.4 gigahertz band, right? So that's why they operate there, and which is why they create the problem, right? I mean, so 2.4 gigahertz band is pretty problematic. 5 gigahertz band is cleaner, obviously. And some of these bands are universal. Others, like in the US, 915 megahertz band is open, but in Europe, 868. So when you sometime buy these devices, they will say European version and American version. Okay, and technically, at least, it is illegal to operate the European version in the US. In theory, yeah.
What will happen if you take a European device and bring it here and just start connecting them?
It will catch fire and you'll get killed. No, no, nothing will happen until someone complains, right? Because so I don't know what is there in the 868 band, but oftentimes a lot of bands in the US are allocated to specific users like fire department or military or whatever, and if they sense interference, they will complain, and then they'll try to triangulate down to you, and whatever. So yeah.
Arrest.
Hmm?
Arrest.
These are civilian crimes usually, right? I mean, these are whatever. These are not.
Not military crime.
No, yeah, but there are exceptions to it. If it's being used by military operation or airport and all, then there would be issues. Yeah. So look, I mean, yeah, I mean, likewise, like if you transmit in the GPS band, you're going to cause so much chaos there. It's illegal, obviously, but if you accidentally do it and all, I mean, it's not like, I mean, they're going to probably, I don't know, I don't have any first-hand experience. They'll probably just warn you, right? So, yeah.
What's the GPS band?
1.4 gigahertz, if I'm not wrong, all the way through early 3. So it's, yeah. So, yeah, no, I'm sorry. GPS is around 1.4, 1.5, and then 1.4 all the way to 3 or 5 is the so-called UWB band, ultra wideband, and GPS often complains about it. So there are often kind of these complaints about kind of is someone interfering with these. Another thing which in last decade or so has got popularity is the notion of white space networks or white space radios. And what they stand for is that oftentimes these licensed bands are not used, okay? And the notion is, if they're not being used, can I use it? Okay, so for example, TV band, okay, it's kind of a huge swath of things, but a lot of those channels are lying idle and many stations don't transmit 24 hours. Or for example, look at devices like those wireless microphones that are used in conference rooms and all, right? There are frequencies allocated to them. Again, if it's not being used, potentially you can make use of it. So that is where this notion of cognitive radios and cognitive networks come in, and the idea is you sniff, and if there is nothing there, and then with appropriate sort of system level mechanisms, you can go ahead and transmit. And what do I mean by appropriate network level mechanisms? For example, a licensed user can transmit saying, hey, I'm here and I'm using it. So imagine kind of a separate band where we can advertise it. Or maybe it's a web server, okay, where I can say, look, I'm using this frequency band in this area, and then if you want to opportunistically transmit there, you can consult it and not transmit. So the idea being that you can get more out of the spectrum opportunistically that way. So that's something Microsoft, for example, has been pushing quite a bit, and this guy's lab does work in Professor Chadwick, the course lab here. So they do a lot of work in that kind of networking, that exploiting available spectrum by sensing its usage and by making use of other resources to kind of coordinate things out. So there are all those kind of things. So like for example, I don't know, some of you might have attended the talk on IoT in computer science, faculty candidate on Monday or Tuesday this week. So he had described this agriculture system for sensing in farms and stuff like that, and that was all based around the TV band by making use of the holes that are there in the spectrum, basically, as in unutilized parts of the spectrum. But these things are like Zigbee and all, just make use of these ISM bands. There are a lot of vendors who make 802.15.4 chips. Your question?
Yes, like cable TV mostly uses wire transmission, correct? So is that still allocated?
That's why it's called cable, right?
Yeah, is that still allocated the same way? Like, could you transmit wirelessly?
There's no allocation there because these are shielded cables, so there is no emission from it, right? So, so they are really limited by the fact that at high frequencies they will not be able to transmit long distances. So cable TV, I think, goes from whatever low megahertz to around 700, 800 megahertz, somewhere in that range. Yeah.
Does it really have that high of bandwidth, or is there something intelligent happening? So like you have 300 HD channels and you can switch anything and you can watch it without complaint.
Yeah, because they have a pretty wide amount of spectrum.
But they're not transmitting all the like all the data for all channels at all times. You're,
But they own the cable.
yeah, but you choose a channel and then you make a link to that.
No, 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 no. No, all the channels are being beamed all the time. Okay, now that's how the traditional cable TV was. The modern cable TV also has these on-demand channels, and what happens? So I'm not talking about satellite TV. Okay, so I guess that's probably what. So I'm making a distinction between cable TV and satellite TV. So cable TV has so much bandwidth that they kind of transmit everything all the time. But what has changed is that they set aside some of that spectrum for internet services. So now you can have whatever TV over your internet service, which is then traveling on the cable TV cable. Okay, which is how probably most of us are doing it. Like I don't have any cable TV subscription, but I do have internet subscription, and I watch TV over that. So I think the world is inverted, but traditional cable TV literally meant that each channel have a allocation. But when you are doing it over the internet, so to say, then your model is correct. That it transmits to you only when you ask for it. Yeah.
What about digital TV? So like I remember a few, I don't know, maybe almost a decade ago they switched.
Digital TV is just a modulation scheme.
Okay, so that
Okay, that was just a modulation scheme. It switched from analog modulation to digital modulation. So that, I mean, it's actually much earlier from 1990s when HDTV came. So first over-the-air transmissions went digital. So every TV station was given a second channel, a digital channel. And then there was a political battle about when the analog channel will be given back, and that happened some years ago because then that channels which were recouped were given to cellular carriers. So around 700 megahertz band, there was a spectrum auction. I think Verizon took a big slice of it because there is a lot of hunger for spectrum there. So that was simply digitization of modulation. Instead of sending analog waveforms, you're sending bits.
To sort of maybe answer the question in the back about the data and all the channels being beamed in, I remember reading, it was a while back, so maybe it seemed ingenious to me at the time, but maybe not so revolutionary right now. But they have a very good way of encoding the data with the signal that they send. They send it very efficiently, and it might be worth looking into.
Absolutely. So look, I mean, how many bits you can send over your chunk of spectrum? I mean, once you're paying billions and billions of dollars for the spectrum, you're going to maximize that. Okay, so absolutely. Coming closer and closer to the Shannon limit in terms of how much data you can pump in. That's been the holy grail, and yeah, huge advances in coding theories and all have enabled that. Yeah, absolutely. And so part of the reason behind digitization was that you could be much more spectrum efficient, right? As digital modulation and compression techniques advanced, you could do it, and of course you can be better quality. So all those gains came from that. So there are lots of chips, microcontrollers around which have the radios built in. And 802.15.4 radio is a pretty common candidate. So you'll find like almost every microcontroller manufacturer also makes microcontrollers where they have this chip on board. And the other very common chip to have is the BLE. So oftentimes you will find microcontrollers which have both BLE and 15.4. These are simple enough radios to integrate. So TI, Texas Instruments, for example, has a family of such microcontrollers, which basically single chip with a radio sitting in the corner, and you're good to go. So 15.4 offers multiple channels, and within each channel they have a protocol very similar to the 802.11 protocol that I described. Wi-Fi is the same way. So there are many channels of Wi-Fi, and then within each channel, so like a particular network will operate on a particular channel, and then use the timing diagrams that I had shown, use those protocols to operate within them. So same story with 15.4. So these are 3 megahertz wide channels, and then your system picks up one of these channels to operate in, and the channel it picks up will probably depend upon the local condition. Like for example, if there is a microwave operating nearby, then some of these channels might be bad, so it will just pick something else. What this 15.4 does allow for is there are kind of 2 kinds of devices there. Devices which are more resource rich, they're called full function devices. They are capable of taking more functions, act as coordinators on the network. They are going to be plugged in typically, and then there are the reduced function devices, which are meant for the battery operated things which can last longer. And kind of the idea is that they play a lesser role. They are really kind of the leaf nodes. So they will not provide routing functionality and stuff like that, for example, okay, because if they're going to duty cycle and all, you will have a problem. So they support only subset of things, and they're designed to be very simple. So for example, now you can buy these light switches which just have a coin cell, and you slap them on the wall, okay. So those kind of things are examples of reduced function devices. On the other hand, a light bulb, since it's plugged in, would be an example of a full function device. And then they have a concept of coordinator on the network. So in each network, there is one coordinator called PAN coordinator, personal area network coordinator. So this is how kind of things would look like. There is going to be a coordinator in the network, and then there is going to be a bunch of devices controlled by or managed by that. Some of these devices could be sort of the reduced function devices, and the others could be resource rich themselves. And you can have kind of arbitrary sort of multi-hop topologies in this system. But again, the idea is there will be some node which is going to be the PAN node, PAN coordinator, which is going to do these things together. More typically, things look something like this. So there are these richer nodes kind of form the backbone of the network, and then the RFDs, the reduced function devices, they kind of connect to the nearest rich device, and you have this kind of hybrid kind of a topology going on. Now the way the MAC protocols and all, so firstly there is a routing layer, which this looks like a mesh, right? So all of that mesh networking kind of stuff gets done out there, but then within a given area out here, right, within a local neighborhood, you are going to be running a MAC protocol. And the way the 15.4 MAC protocol works is that at a high level, there is a periodic structure to it, okay, and they call it super frame, okay. And then the idea is that in this super frame, there are a few different kinds of subframes that exist. So at the very beginning, there is in this red color, there is a network beacon packet. Okay, so at the start of the frame, this beacon is sent out. This is sent out by the coordinator node. Okay, so it contains information about the network, kind of variety of things and all. Then there is this additional period which is called beacon extension period. So some bit in the beacon will say there is a beacon extension also coming. In this beacon extension, you give information about like essentially passing information back from the coordinator to kind of these other nodes, like things like, oh, is there a message pending for you? Okay, so you can think of it like this is where we put in information relating to how rest of the resources are being scheduled, and I'm going to come to that for a moment. Then there is this whatever yellowish creamish color area. This is the contention period. In this phase, during that period, essentially you operate kind of like 802.11 protocol, okay, CSMA/CA. So you compete, okay, there's nothing reserved for you. But then finally there is this green period, which is by reservation. So during this time, there are slots, and slots are reserved for specific units. So this is where, like if you have a microphone there or something periodic, you would put these things out there. And it is a management of this, which is done through information passed in this light blue color thing. Okay, so essentially it's kind of a hybrid thing. We allow for these contention-based things, which is super simple to implement, but then we also support kind of traffic which is more regular in nature, and you want to give it some sort of guaranteed properties. So that's how kind of it looks in its full glory, except you can also operate it in simpler modes. Like for example, you can operate the network without beacons, without any of this, just as a pure contention system, because that's a strict subset, and therefore is a valid 15.4 system. So typically what would happen is a device, after you have paired, will wake up, would look for the network beacon, and then follow kind of the protocol that is happening. It has lots and lots of features. These protocols are pretty complicated. I mean, these are like thick books, okay, and then the chips have to implement it. So kind of lot of details have to be specified precisely so that different vendors' products can interwork. That's a very important part. It's no good if your system works, if your 15.4 radio only talks to your your own 15.4 radios. So they have a whole bunch of other things also, like for example, they have a special mode called battery life extension mode, but the idea out here is that you let the things duty cycle here. And as I guess you had asked the question, like it competes with Wi-Fi for the bandwidth. So when these new things are proposed, a lot of effort also goes on understanding how much harm they're going to cause to each other, right? Could they coexist, for example? So quite possibly the way these systems can work is in a given home setting, you have kind of a wide, you have a bigger chunk of the spectrum. So there are several Wi-Fi channels, and then you have a lot more Zigbee channels. So maybe what you could do is you can allocate your Wi-Fi and Zigbee channels smartly so that they don't non-overlap within that region, right? So you can do those kind of games also. Lately, some work has also begun to look into things like, can the same radio also simultaneously handle multiple of these kind of packets? Okay, so people have shown, for example, that Wi-Fi receivers, they can coax them without any changes actually. Okay, they can coax them into being able to hear 15.4 packets also. Okay, so there's some cute work of that nature. It has limitations, but it turns out that there are ways you can get these things to kind of help each other out also. The next one before I go into Bluetooth is this ANT, which I mentioned. So it at this stage is more of a historical oddity, historical thing, because it's been basically taken over by BLE. But it was interesting in its time because it basically went after this regime of very low power, very heavily duty cycle, relatively low rate systems, essentially sensors and all. So products in the fitness, health, medical, that market kind of went after. And so microwatt, many years of battery life, these kind of things. So if, some of you might recall products like early days of iPhone, Nike used to sell some attachment for your shoe, for example. So that was ANT. So actually, many of the Bluetooth chips which are sold now are capable of ANT. Okay, and some products kind of exploit that also. Your iPhones actually, until when, I don't know at present generation or not, but until a year or two ago, the iPhones did have ANT in it, even though it's not advertised that way. So ANT radios also, as I mentioned earlier, in treadmills and all. Okay, so if you just go back to like 2-3 years ago, ANT was very prevalent out there. This one also was sort of a mesh network, okay, and but it was not designed like Zigbee to have this global synchronous mode. So it's basically another, Zigbee is lower power relative to Wi-Fi, and this is another sort of, let's say, 10x lower in terms of the power it is aiming for. So one crude way of thinking is Wi-Fi is for watts level power, Zigbee is for milliwatt level power, and this is for microwatt level power. Okay, so kind of that's how these things are. So a lot of sort of variety of modes supported, even things like transmit only sensors, okay, which cannot handshake or do anything like that. They just will blast out data. So ANT sort of went after that. So years of lifetime, if you may, okay. And these slides kind of show that. I'm going to skip most of these because they're probably at this stage no point. Yeah, I'm gonna skip these. Okay, so what happened some years ago was that I guess at this stage maybe 6-7 years ago when BLE first came out. Yeah, so Nokia used to have in-house proprietary very low power sort of thing, protocol very similar to what was ANT, and basically they pushed it and it became the Bluetooth Low Energy. So the protocol is very different than standard Bluetooth, but it's under the same umbrella. And I think part of the way of thinking about it was more of a marketing thing at some level, in the sense that if they had called the original name, which I think was Wiptree or something like that, okay, WIBTRE, no one would have cared. So it's like any radio standard, if it is called Wi-Fi or Bluetooth, is going to have a higher chance of adoption than if it outside those umbrellas. And same thing happened with sort of BLE. So much like ANT, these are design. BLE was also designed for short burst of data and over months and years. It is, from what I have read in papers and all, less efficient than ANT in doing that, but ANT was basically proprietary, not a standard, much like Z-Wave, whereas this is an open standard and therefore and got built into all the phones. Okay, so so that sort of helped it a lot. So let's take a 5-minute break, and then I'm going to talk about Bluetooth LE, which basically at this stage, for let's say the last 10-meter type networking for sensors and all, is pretty much the dominant technology. Okay, so of interest from that perspective. Okay, so let's take a short break.
I have a question.
Mhm.
Have there been any work on like a universal radio that doesn't care about what, kind of like how what you said before, where you sniff to see like what
Software radios.
So those are basically the closest thing you would have to a.
Mhm.
Okay.
Yeah.
So it would, like, I don't know, if you're like in the army or something, I don't think you would care about breaking the laws
No,
of the
yeah,
foreign
yeah.
country that you're in.
And actually, so Army cares a lot about these flexible radios, because when they are in coalition settings,
Mhm.
right, interoperating with different
Yeah.
countries' militaries, then you want to be able to reprogram your radio to hear different waveforms, as I like to call it. Okay, and then the other thing is, even within the US, different agencies use different radios, and also when they converge in response to a disaster and all, right? I mean, it used to be that they couldn't interoperate, and so you would hear these kind of stories that soldiers are making use of their personal cellular phones and all to
Yeah.
communicate. Okay, so those are examples. So you have these costly but siloed
Mhm.
radios. So again, a lot of emphasis on creating. So Army has that, like whatever, DoD has had these literally multi-billion-dollar programs for creating radios which are
Universal
like
radios,
universal
yeah.
radios in that sense. So there's a program which I think still goes on. It's called JTDR, Joint Tactical something radio.
Mhm.
Okay, but it's basically a software radio which could, or let's say
Program any
software-defined
frequency.
radio to which you can give different waveforms, and it can work that way, or even simultaneously interact with.
I was curious also, like, I mean, wouldn't you want to also do a sweep? Like, let's say you're in a new area, like some frequencies may work better than others, and it's very hard to tell which ones would be best.
Absolutely,
You
absolutely.
just want to sweep through the whole spectrum and see what works best.
Yeah,
and then latch on to
absolutely.
that.
Yeah, there are all reasons for it. Absolutely. Yeah.
I had a question about ARM. Are you aware if it can stream data of the heart rate and the cadence at the same time?
Which device
The Hexiware.
can it
Can
stream?
it stream both at the same time?
So see, the way it works is that short answer, yes, right? Because what it's doing is it's publishing it, and then your Raspberry Pi has to fetch the data, right? I mean, so it's not streaming in a strict sense anyway. What you're doing is you're going, and so there's a register where you update the reading, and then every time the, let's say, a phone or Raspberry Pi queries it, it fetches the latest value from there. So sure, it can do that. Yeah.
Oh, okay. Because I
Yeah.
just I was playing around with that.
Now I don't know
Yeah.
what you mean by cadence. Are you referring to
The step.
the step file, right?
Yeah.
Yeah. And there is one field there where you can put your own put your own custom values also. So think of it like the following. There is, some of it will become clear from this lecture actually, that there are a bunch of key value pairs, okay, and most of these keys are fixed, like there's a key saying heart rate, okay, and then the subscriber can say send me the latest thing. So you could do that, but then there is so a couple of ways you can do it. One is you can cheat. You can say, I will just use the temperature thing to actually send my step count. Let's say, or whatever, any other value that you wanted to send. So essentially it's giving you a bunch of slots, and you can put values in there, and then the receiver or the client, which is your Raspberry Pi, let's say, it basically just reads it. So whatever it reads, it's going to get it. But there is a set of values which in your software you are updating.
Okay.
Yeah.
And so I assume it works just as well with Android.
It's the same with Android or
yeah.
anything. Yeah, it doesn't matter what the client side is. Yeah, just wait maybe the rest of this lecture, and some of the Bluetooth concepts will get clearer. Yeah,
Okay.
sure. Okay, let's start. So, wanted to do a bit of a deep dive into BLE. For some of you, it might even be useful to, from a project perspective, to kind of see what goes on under the hood in BLE. Some of the concepts are a little bit convoluted, unnecessarily at times, just jargon. What I'm describing is going to be more BLE 4.0. Mostly because 5.0 is pretty recent, so I don't have information on that.
Bluetooth, can systems that use Bluetooth Classic pick up BLE signals? Not send, but pick.
What do you mean pick? Yeah, I mean they're the same radios.
Yeah.
Sure. It's the same radios, but you can almost think of there are systems which only speak one, only the other, or both. But like there are chips which only do one, there are chips which do both. So I don't know how quite to answer your question, because deep down certainly they do share hardware, but then the actual protocols are quite different. You can think of BLE is built around the set of packets which were used to set up connections in the classic Bluetooth. That's one way of thinking about that. The set of messages that were used by Bluetooth for connection setup are what are being harnessed for a different purpose for purposes of BLE. Okay, so BLE or Bluetooth Smart or kind of a whole bunch of names is basically a subset of the overall Bluetooth specification, and but its lineage is quite different, as I alluded to before the break. It basically was targeting the ANT market segment, namely extremely low power point cell type sensors and things like that, or even like wearables and possibly sort of other type of deeply embedded things, or even sort of disposable devices and such. Some of you may have seen these devices which are like tags for your luggage or your keychains, and also that they are not lost. They're all BLE based. So that's the kind of market you're looking for, or even car keys and all. Okay. Its peak rate is megabit per second, but in practice it's really what you get out of it is 5 to 10 kilobyte per second. Okay, so it's pretty low rate relative to kind of like your classic Bluetooth, full-blown Bluetooth, where you can do high quality music, stuff like that, right? I mean streaming media and also kind of different. Very short range connection. Essentially, good way of thinking about it is really meant for room level connectivity. So that's what it's target is. And again, they come in a variety of power ranges. So there are devices which are literally meant for like centimeter scale stuff to things which are, let's say, small number of tens of meters. So there are a couple of reasons why Bluetooth is even more interesting than the classical full-blown Bluetooth. So one is obviously the power side, but the other is how open it is. Okay, so particularly on Apple devices, remember classic Bluetooth existed before BLE came out. So Apple, just like they required manufacturers who connected to the iPhones through the cable to buy a special security chip, but really, I mean, whether security was the main motivation or just monetizing was the main reason. Point was that you couldn't just design something and have it talk Bluetooth classic, as in to the iPhone. So, like for example, when you see serial devices connected over Bluetooth, it's really over the classic Bluetooth. There is something called a serial profile, and for you to be able to have your product work with the iPhones, you need to put a chip which you can only buy from select vendors. And before you do that, they ask you to provide proof that you have the appropriate license from Apple, and that license costs a lot of money, as you might expect. So you couldn't do those kind of things. BLE, on the other hand, had a very different approach. So basically, you can design a BLE device and just have it work openly with iPhone, and of course, Android was always open, and a whole bunch of other things as well. So, and ironically, I mean, Apple came out with support for BLE much before Android did. Okay, so more robust support and all. So essentially, it got blessed because of its low power characteristic. I tend to think that the reason was basically classic Bluetooth was just way too hungry. It was very easy to design devices which would do pretty bad from a power perspective. So whereas BLE has pretty good characteristics from that regard. So it's essentially, the nice thing is it's kind of universal, both in the sense of being built into the platforms, but also in the sense that as a peripheral manufacturer, you don't need any special chips or anything like that. You can just go ahead and design and work. So it's universally there. Okay. Another advantage of BLE is that it has a mode where you don't need any pairing. So you can essentially exchange data, limited amount, but you can exchange data with devices with whom you don't have any prior pairing process. So remember, like, I mean, when you do things like Bluetooth speakers or headphones and all, you kind of go through this pairing process, which is essentially they exchange some cryptographic keys, and like you end up pairing, so that you are really sort of you cannot sort of send data to the wrong device and stuff like that. So BLE does have that mode, because sometimes all you care about is there a temperature sensor here? What's the reading in it? Okay, you don't like you walk into a new space or whatnot, right? So that becomes very easy. And the other aspect is synchronization time, as in how long it takes for you to establish a connection before you can exchange data. And we saw a number in the earlier slide said that classic Bluetooth is like in seconds, and that's painfully slow, because 3 seconds, I mean, 2 cars can pass by, 2 humans can pass by, you wouldn't be able to pair during that time. So BLE offered a lot of these advantages. Okay, so what is it? So a few terms out here. So there is a client which needs the data, and there is a server which has the data. Guess who is the client, who's the server? So in Bluetooth, that becomes a little bit intuitive. Normally, we think of server as a big thing and the client as a small thing, but it's the other way around out here. Your temperature sensor, that puny little Bluetooth tag, is the server, because it is what has the data, and your phone is the client. Okay, so if you think from a server-client perspective, then in Bluetooth terminology, your iPhone or Raspberry Pi or whatever Galaxy phone, they are the clients, and they are the resource-rich entities typically, okay? And the servers are these puny little things which have the data. But then there is a separate set of jargon which really are perhaps the more appropriate one to use: central and peripheral, okay? So central is the entity which in Bluetooth jargon is kind of playing the role of being, I guess, the center of action that collects the data and stuff like that, okay, and peripheral. So peripheral equals to server, client equal to central. Now what happens? So essentially, what Bluetooth LE did was, like I said a few minutes ago, they leveraged the messages that classical Bluetooth used for establishing the connection. So the way the connection would be established is that what happens like when you try to pair something with your phone. How does it work? Anyone? Put the device into pairing mode, and then it detects something, then it says, does the same number appear in both places and stuff like that. You kind of go through that process. What's happening under the hood is when you put your device into the pairing mode, and meanwhile you have turned on the peripheral, then the peripheral starts transmitting some sort of a packet, beacon packet periodically, and your phone listens during that mode, okay? And then kind of the pairing so it's scanning, right? So that's how the pairing happens. That's exactly what they make use of in BLE. Okay, so essentially the broadcaster, which is that peripheral, the server, it basically transmits advertisement saying, I am here, I'm here, I'm here, but it does so at some duty cycling interval. Okay, so that little tag on your luggage, all it is doing is just transmitting these advertisement packets, okay, which are exactly the same packets recycled from the pairing messages which in the classical Bluetooth. And your phone, the client or the central, basically scans, okay, and listens to this advertisement, and this advertisement can now carry stuff in it, okay. It can carry even data in it besides kind of identity information and all. So this becomes kind of a nice way where without any prior sort of agreement of any form, you can provide some information, you can publish information, right? I mean, you can there could be a beacon out here saying whatever, this is room number X, or the projector can advertise, okay, so that you can pair. So that basic ability is there, okay. So it's an ad, literally, okay. It's advertising, it's pushing information out.
So,
yeah.
Like, let's say like client connects to a server,
Mhm.
and there is an active data transmission going on. So is one of the devices, are they still in pairing mode?
You're talking about classical Bluetooth?
No, this
There's no pairing here, right? All is one device sends out these periodic ads, and the other device scans for it at some time.
So in theory, like between sending two packets, it can also connect, like talk to some other device.
Which device? This guy can talk to a different device?
Yes.
The broadcaster can talk to another device. In theory, yeah, but the thing is, these are very low power devices and all, right? I mean, they're designed to publish data infrequently.
And then
In classical Bluetooth, they build upon top of this for purposes of that pairing I was describing, right? So during the pairing, what happens is, like after this, you can establish a connection. Okay, and we'll see that even in BLE mode, BLE also, there is a connection mode also for additional data transfer. But at this point, all that's happening is that the server devices are basically sending out these ads. Those ads have some particular format which can even capture some information in it. Okay, so like for example, many years ago, I don't know, 4 or 5 years ago, Apple had kind of made a lot of noise with this thing called iBeacons, and iBeacons were nothing but BLE devices which are transmitting these advertisements, and in that they were carrying some specific pieces of information which Apple had defined. Okay, so the format, the payload can be defined by a particular class of device, for example. and we'll see kind of what kind of things could be there in it. So this is the basic advertisement, and you can have this advertisement take place in multiple channels. So a single device can broadcast on several channels. So there are several Bluetooth channels which are set aside for this purpose, okay, for this kind of advertisement. And the observer can again scan in multiple channels. So the idea is that you increase your chances of pairing up, so to say, or whatever, being able to send the data by transmitting on multiple channels. Okay, so then and in many systems this is where you end. Okay, that you just send it the beacons, it contains the information, and kind of this device is happy with it. So in these iBeacons and stuff like that, or even your luggage tag scanners and all, that's sufficient. I've observed the tag, maybe it will carry some unique string, so they often carry what are called as UUIDs. Anyone knows, have seen it, UUIDs, right? What are UUIDs? Right, and it's basically a way to uniquely identify every subatomic particle in the universe. Yeah. Okay, but essentially the UUID is lets the application running on the observer to then index a database and find more things about it, right? I mean, so this thing doesn't have to transmit anything more than that, but you could also transmit other stuff in it, like maybe the temperature value, some small amount of data, because this is pretty tiny little packet. Okay, so now that's not where it just ends. You could go ahead and then set up an additional connection. This is still a BLE connection. Remember, we are in the world of BLE, so just forget classic Bluetooth at this point now. So you can set up additional the connection request, and this is the only way to send data downstream. That is the only way your iPhone can send the data to the device, for example, to, let's say, configure it, or perhaps to cause an action. You know, there has to be a connection request. Okay, because remember, the beaconing part was just one way, but once you set the connection, then you can have richer data exchange happening between them. So after you have set up the connection, you can push data to it and all. So even these most trivial of the beacons and all usually have a mode where you might want them to be programmed with something, like maybe you want to program a new UUID, or maybe you want to give them some name or whatever, right? I mean, you want to program that connection. So you could use this, or perhaps some other out-of-band mechanism for that purpose. So so there is that ability to set the connection, and that's the only way you can then have downstream information going through. Then each one of these things are going to have additional parameters. Remember, the idea is these are low power devices, they're going to go to sleep. So these crucial things like advertisement interval, connection interval, like how once I establish the connection, associated with that connection is going to be an interval that only at that that gap, that time interval, would the information be exchanged. So this is not connection in the sense that now you have a permanent thing, whenever you feel like can send the data back and forth. That's not like that. It's basically an agreement that every so often we are going to exchange the data. So that's the notion of connection interval. Now, what can happen in these scenarios? So when you are in this mode of broadcast advertisement, then multiple things can listen to it. So if there is a beacon out here, my phone can listen to it and your phone can listen to it, and we can both detect whatever the temperature in this room, or the fact that there is a projector or whatnot. Once one of them creates a pairing relationship, then that is with respect to that particular central only. So you can have a central device which is paired with multiple peripherals. Okay, so the basic discovery you can do, so I mean, try it on your phone. If you just go to App Store or Play Store and just type BLE, okay, you'll see a lot of these apps from TI and these kind of companies. They basically let you browse what devices exist around you, and what they're doing is they're just listening to these advertisements and I'm giving you information. And these advertisements usually have enough information to tell you what kind of device it is, what all it supports, stuff like that. Your ability to pair is kind of a different story, okay? That may or may not be allowed by the device. Like those of you who are using Hexaware, there's a particular code you have to use for that pairing to work. So you certainly don't want a random device to go ahead and program this thing. So for certain class of devices, pairing where you need to send information to them and where there are security considerations, like for example, maybe the baseline information can be pushed out in the advertisement, but the more private information you will only push out after the pairing has been done because some authentication would have taken place at that time. Okay, so diving a little bit further under the hood, a megabit per second error rate, but remember in this game error rate is kind of some never achievable peak number, okay, because by the time you are done with your math protocols and overheads and coding and all sort of stuff, you get a very tiny number. It uses GFSK modulation, so it doesn't really matter, some choice. Main thing though is that GFSK modulation allows for very simple circuits, radio receivers which can rapidly wake up, which consume which are very efficient in terms of power consumption characteristics. Moreover, they use much like the classical Bluetooth, it uses something called frequency hopping to avoid sort of interference. So last time I had talked about that how if multiple communications have to exist in the same region of space, I can separate them out in frequency. I can separate them out in time using these protocols, but there are a couple of other ways you can also separate them. One is called, well, there are a bunch of ways that fall under the umbrella of spread spectrum. One of them is called DSSS, but the basic idea is every time I need to send a bit, I'm going to actually send a faster or a longer sequence. So like let's say 1 corresponds to some code, 110010, something, and 0 corresponds to kind of some other code. And whenever time comes, I'm going to send this. But the code for my one and the code for your one are orthogonal. So we can both send it over the air and the receivers can still correlate and distinguish them. I'm kind of very hand wavy out there, but think of it like there exists this higher dimensional code space where I can separate things out. Okay, so multiple transmissions can concurrently exist in the same frequency, in the same time, but they are separable still. And another approach to achieve the same thing is called frequency hopping. So I have a bucket of frequencies and I'm going to have a unique hop pattern. So maybe I'll say I'm going to transmit at frequency F1 first, and then F10, and then F3, and then F7, and I'll have some sort of a hopping pattern, and so would you. And the idea is we are both simultaneously kind of concurrently doing the same thing, and because we are following these random patterns, so then the collision probability is going to be minimal, and that's called frequency hopping spread spectrum. I'm sure you may have read the stuff, but interesting little tidbit about that the frequency hopping spread spectrum was invented by a Hollywood actress back in late 1930s. So she held the patent on it. So that was kind of interesting. So Bluetooth uses that. Okay. So these transmitters hop around, okay, in frequencies very rapidly. So send something at this, then move to another one, move to another one. Military uses frequency hopping quite a bit to evade jammers and evade detectors, but in this case the purpose is to evade interferers that might exist and just for multiple things to coexist at the same time. So that's the frequency hopping part, and then there exist many channels in this domain, in these systems, and 3 of them are dedicated for the advertising function. So that was classic Bluetooth, and BLE just makes use of that. So essentially, this is what allows you to discover devices, and when a connection request happens, then the same channel is used for handshaking. So these are all what in networking parlance are called as signaling messages. You're kind of participating in some handshake protocol to exchange necessary information. Once you do have a connection, then that data exchange takes place in the main channels, the main data channels. So these channels are just used for purposes of the initial advertisement, and also in this case, for example, you kind of see the red channels are the advertisement channels, the green channels are the data channel, and you kind of, the transceiver has to sort of switch back and forth. Okay, so another jargon in Bluetooth and actually in many other standards that you would see is this concept of profile. So what profiles do is they collect, you can think of it as a particular way of using that protocol for a specific purpose. So you will hear terms like serial profile over Bluetooth. So that's basically how devices following serial data communication protocol, like color of sensors and all, high rate sensors and all, would follow. So profile is just generally, there are USB profiles, and so just like that, there are profiles out here also. So one important profile in Bluetooth, overall Bluetooth, is something called generic access profile, GAP, and that is what is used in BLE for that advertisement purposes. So it is what makes that whole process of advertisement and connection establishment and all sort of obey. So kind of the basic purpose is this is how handshake happens, to discover each other, set up the parameters of one's connections and things like that. And in this context, then you have the peripheral devices that I mentioned earlier and the central devices. So some devices are capable of playing both the roles, and some devices can only play one role. So kind of like 15.4 and kind of like ANT, which I didn't go into that much detail, peripheral devices are kind of the ones which are resource constrained, so like Hexaware is an example of a peripheral device. But then you also have devices which are the central devices. They are capable of doing that scan, and usually these devices are also capable of being peripherals themselves. Okay, so usually these devices, like your phone and all, can operate in both modes. They can be peripheral to another master, or they can to another central, or they can be central themselves. So the Raspberry Pi, your iPhone, your Android phone, they are kind of examples of this. So this whole advertisement and scanning stuff that I described earlier with those figures is really defined as part of this GAP profile. And there are two ways to send advertising out in this. So for your peripheral device to push data out. So one is when the device is simply sending out these advertisement packets, it can put some payload in it, and that's what your iBeacons and all do. So that's the advertisement payload. And the second thing they can do is when they respond to the scan request, which was a follow-on packet, then there is additional information you can send out. Okay, so you think of it like this: I'm advertising, and then if you do a scan request, I can send you some additional information. So advertising data payload is mandatory because it is basically blasted out to the world. Okay, so this is kind of like your billboard. Okay. Whereas the scan response is optional, and one way of thinking about it is this is a way you send more information really to a specific device. Okay, so this is where you might, so like it could be like you hear a device and then you kind of query it more. Okay, what else? Tell me something more about you. Okay, or value of a particular sensor and whatnot. But remember, you cannot send any information in the scan request. So still, this is only information from peripheral to the central. Okay, so so this kind of what is going on out here. In this case, the central is at the bottom, so peripheral is blasting the advertisement, and then the some central at some point might say scan request, and then the peripheral will send additional information out there in this packet. But this packet, scan response going back up, cannot carry any information. There's no provision for it. So still, the information, meaningful information flow here is still from peripheral to the central. And what these advertisement intervals are and all are all configurable from milliseconds to seconds, or possibly even more in some systems. So obvious connection back to battery power. So these beacons and all, like iBeacons, and Google calls them Eddystone, I think. They're all kind of basically doing this advertising at some sort of periodic interval, and you kind of an obvious battery life and latency trade-off, right? How long it takes to detect it versus how long the battery life is going to be. If a listening device, namely your phone or Raspberry Pi class devices, if they're interested, then it has to explicitly kind of request, and then the peripheral will provide it with additional data. Okay, so that's how sort of this process works out. The topology, the way it kind of works out here is kind of like a star network, right? I mean, in this case, the peripheral is blasting things out, and the iPhones and all these kind of devices are looking to it. So the way this information is structured and organized and all also follows some very specific rules that sort of Bluetooth standard is described, and we are going to go into that a little bit later. And that takes as part of that whole connection that you have established. But there are many cases, many interesting class of devices where all you just want to do is advertise the data, right? So the iBeacons and all fall into that category. And a lot can be accomplished. And like I said, if the data being sent out in the advertisement is something which then carries some special application level meaning, then you can consult a database. And also you could imagine, like, one of the ways these iBeacons were being used was that when you program the iBeacons with a particular UUID, so there might be a UUID for, let's say, Macy's, and Macy's will then also, Macy's app would obviously knows that UUID, and there's nothing secret about that UUID. So the Macy's app knows that UUID, and then the idea is, or perhaps a set of UUIDs, and anytime and then the Macy's app will tell the operating system, I'm interested in this UUID. I'm interested in any Bluetooth advertisement packets which carry this UUID. And what the OS will do is every time it hears it, it pushes it up, and that way the app will know that, okay, I'm near a Macy's beacon, and then it will go and consult a database and then push ads at you or whatever. Those kind of things can begin to happen. So those are the kind of scenarios, and you can kind of layer on top of it other things like cryptographic stuff and all. One of the nice things out here is that the beacon doesn't know that you are near it. Your phone knows that you are near the beacon, but the beacon doesn't know that you are near it. Okay, so from a privacy perspective also, there is kind of a certain attractiveness to this kind of approach. But then there are also sort of other security risks, like I can make you think, your device think you are at you are near something like in a Macy's store when you are not, for example. So that it can create security or other kind of annoyances also. So then you therefore need some additional sort of application level logic to kind of deal with it. So what happens in these broadcast packets is there is a small amount of data that you can send, 31 bytes. So not a whole lot, but actually if you think about it, there's a lot of useful stuff you can still carry in those 31 bytes. And what Apple's iBeacon and subsequent similar things from other players did was that they basically created a custom payload, which is really the iBeacon standard, if you may, from Apple in that main advertisement packet. Okay, and in particular, in that packet, there are fields which are left open for the manufacturer. So they basically co-opted those fields for purposes of the iBeacon protocol. So what's happening now is these beacons, these peripherals are advertising. There's potentially a whole bunch of central devices which are listening to it. And once a connection is established, then the advertising process will stop. So basically what happens is, let's say one of these central devices says, okay, now I want to connect with you. And then at that point, you have become paired with this. And then at that point, that regular beaconing will often stop because the pairing has been done, or at least in a classical Bluetooth setting. I think beacons and all will do that only for purposes like programming. So, for example, most of these beacons establish a connection with your phone so that you can push firmware updates to them, for example. Okay, so usually some of these devices would say, like, after you put in the new battery, then for a while they will be in this other mode, okay, so that you can do reprogramming and all. But in the normal mode, there's just one-way transfer of packets happening. So that's the basic sort of advertisement structure. So next question is, how is information represented within these things? So what Bluetooth uses for capturing these information and all is a concept called service and characteristics. Okay, it's, as we'll see maybe next time because I'm coming close to it, it's kind of a fancy way of saying it's like a key value data store. Okay, the peripheral has bunch of like slots which have names, the keys, and it has some values in them, and when you establish a connection, then you can go ahead and query these things. So it's kind of structured around that, or think of them like registers in a device, and you are able to query those registers, read and write those registers. So some of those keys may be readable only, and some of them may be readable and writable. Okay, so that's how you kind of structure them. Yeah.
What would be the difference then between a publisher and like two nodes that are interacting in a service, like publisher, subscriber, and then service?
Okay, so peripheral would be the publisher. Okay, and it will publish according to certain well-recognized profiles. So like all heart rate sensors publish using a profile which is relevant to heart rate sensors. And anyone complying with that profiles has to provide a certain set of key values. And once you establish a connection, that's what you're querying. On the other hand, let's say, I don't know, like a robot may have a writable attribute, like next destination, for example, or a command or something like that. So you could kind of structure it that way. But all of this is really relevant to the peripheral side, and the central side is just reading and writing. So that's kind of the user for this thing. Let's stop at the stage because I don't want to start this that I cannot finish. But we'll sort of see that. And also the links, I had sent around on Piazza, I think last week, kind of some links around things. So one of them kind of takes you to code and all, which you can run on Raspberry Pi and talk to these things. And there are fairly reasonably done Python packages and all, and there's a lot of open source code and all around to kind of write your own sort of interaction with these devices. Okay, so see you tomorrow.